And this angle here, angle C is equal to twice angle B, yeah? This is problem 25, probably from PST or something. And the condition was that you had a point P inside it, such that you had a whole bunch of isosceles triangles. This was isosceles, and this was isosceles.
When is shipping the computer? Where is this question from?
Johnson gave it to me, but I think it's from PST or something like that. So you basically got a point P inside here, right?
Such that they're isosceles?
Such that, yeah, this length equals that length equals that length, right?
What's the AC, the funny thing on AC?
That's the side of the triangle.
Why is there two lines?
Two lines.
Like, what's the upper thing?
Yeah. What do you mean?
Like, is that the arc AC?
No, it's the line AC. It's a segment.
Okay. So you have it, so it doesn't. Oh, okay, sure.
Yeah, so the question says to prove BAC equals 3 times PAC. Yeah.
What BAC? It's 3.
So another way of saying it is BAP is 2 times angle PAC. Yeah. So I sent this at like 5 p.m. yesterday. So if people wanted, they could have tried it before they did the test today. But or you can try it later and look up the solution again. But I want to present Will's solution and my solution. Will's solution. So Will sent a solution, and I had a solution. Okay. So Will's solution went something like this. So you extend the angle bisector to that side, yeah?
Angle BAC is 3 times PAC.
Yeah. So I guess the point of doing that is, let me just draw it again. So the point of doing that is because angle C is equals twice angle B, right? The angle bisector makes an isosceles triangle here.
Angle C is twice angle. Wait, is that given?
Yeah. And so if that happens, right, it actually makes a nice angle thing there, and P is collinear with this perpendicular bisector because they're both isosceles, right? Let me just draw that in. So actually, if you take the perpendicular bisector, then P actually lies on it. Okay. This is P, this is D. Yeah. So if you let this angle be X, this angle's Y, this angle's Y, this angle's Y minus X minus Y, and this angle is X minus Y. Yeah. So what you have is so he did it basically the kind of the excess brain power way. So
What's the excess brain?
use similar triangles and angle chasing only. So it just requires a lot of athleticism. Okay, so you got the triangle A. So can you see that this angle here is 2x? Yeah. And this angle here is x.
It's 2x. Yeah.
Yeah. So he showed that triangle ABD is similar to triangle ABC, yeah? ACB. So they're equiangular, right?
2x. Yeah.
Yeah. So if you take the ratio of the sides, AB on AC has to equal AD on AB. Yeah. Yeah. Then he shows that angle A. So then she shows that angle triangles ADP. And shows triangle ADP is similar to triangle APC. Okay. So the included angle is the same, right?
Yeah.
So he just wants to show the ratios are right. So the ratio comes from the isosceles condition. So AB equals AP, right?
Yeah.
So you just sub in AP equals AB into the previous ratio condition. So AP on AC equals AD on AP. Okay. So AP on AC and then AD on AP is the ratios of the two triangles, yeah? So they're similar, yeah? Okay, using that they're similar, he gets expressions for angle APD is x minus y. You see that?
Yeah.
Because they're corresponding angles. Yeah. So you got x minus y here and x minus y there, yeah? They're equal. So then he angle chased. So for example, can you see this angle here is 90 minus x, right?
Turn the laptop over.
So this is 90 minus x there, right? Angle D, CDP, yeah? is 90 minus x. So that makes the angle at A, PAD, its exterior angle, it must be 90 minus 2x plus y. Yeah? The angle there. Because the exterior angle is that angle plus that angle, right? So just do 90 minus x plus y. Okay. Okay, then angle chasing the other way, you get this thing here this is isosceles, so this is 2x minus y, right? This is isosceles. And so that angle here is 180 minus 4x plus 2y, yeah? By angle sum. And therefore, this expression is twice that expression, right? So then the angle's triple. So this 180 minus 4x plus 2y is 2 times 90 minus 2x plus y. Yeah. Okay, and that solves the problem, yeah? So actually, I wanted to talk about my approach to it. Because this problem looks really easy. It's actually not as easy as it looks. And if you're looking at the solution, it maybe looks really easy too. But it's actually pretty tricky. Okay. So we'll seem to overcome all the trickiness by essentially brute force. Okay, so it's very good. Yeah. So something about this problem. So me and Johnson first angle chased through the triangles, yeah. And the thing you notice is when you angle chase it, it's not enough, yeah. So you can't get the last angle right without just an angle chase. So it makes sense to talk about sides, and that's how you get different angles using similar triangles, right? Okay. And if you do angle chase it and you set the two conditions equal, what you need it to be is like you need like x minus y, or you need like basically like um x to be like 60 degrees or something. It was like some very special condition relating x and y, you know? And it was kind of interesting that it should come out just from P being inside the triangle. You know what I mean? And so something about it just being on the other side of the triangle was enough. So I didn't get anywhere until I could draw the diagram in a different way, you know. So that key to the angle bisector was a key step, yeah. So the key to drawing triangle B D C was a key step, right? And call that E. Okay. And I guess it's a key step because it really captures the symmetry of the problem. So that's like some sort of axis of symmetry. And it seems kind of crazy that no matter where you draw, yeah, so instead of doing D, right, we do P first. We do P first. And it seems kind of crazy no matter how you draw an isosceles triangle here, right? Okay. You draw an isosceles triangle any way you want, right? As long as the tip goes above the P. Okay, so okay, I need to draw this thinner. So you could have a really obtuse isosceles triangle there, right? This is B, P, C. Yeah. And the kind of question becomes if you draw like this, it's basically like no matter how you draw this isosceles triangle here, right? Yeah. As long as it's kind of high enough to get above P so that this joins to be a triangle, then you can always close it off here and have this be an isosceles triangle.
The reverse reconstruction.
Yeah.
Okay.
That makes sense. Yeah, so and the fact that the angle is there only depends on P being inside the triangle somehow.
What makes... Wait, what's the isosceles triangle?
So this is APB is isosceles, and BDC is isosceles. Yeah. So the fact that yeah, the diagram, like if you reverse it from the symmetric isosceles triangle, it seems kind of crazy. Like no matter where you put that up, it always comes out to be half the angle there. Yeah. So for some reason, this angle is always twice this angle. Yeah. Okay.
Very weird.
Yeah. So to take full advantage of the symmetry, right? What you could do is you could actually reflect it about this middle line. Yeah.
Oh, then do you get like the angle of the center?
Across what?
So across here, yeah. Yeah.
Yeah.
Okay.
So you get people here. So you reflect it there, right? And these angles are the same. So now it does look like the angle at the center thing, right?
Yeah.
See? The angle, because it's basically the same arc, but it's just somewhere else, right? But once you reflect it, they're standing on the same segment there. Segment PC. See, now this angle is half the angle standing from A, right? A prime. And actually, because you know it's isosceles, right? A is the center of that circle.
Yeah.
Yeah?
Means A prime is also equal to...
Yeah, so it suffices to show, or you have to basically show
Yes.
that AA prime, that AA prime is equal to AC, right? A prime C. Yeah? Because then they're on a circle and it actually is half the angle, right? So you basically just have to show that AA prime is equal to these lengths, right? Yeah. But this is way obvious now because this is angle bisector, right? Yeah.
Yeah.
Because this is the angle bisector. And this
Why isn't it?
is the definition.
Oh, we defined it.
Oh, and...
Wait, which angle? Which line?
BD.
BD.
Oh yeah, that's like an isosceles trapezium, which is cyclic.
Where?
Because like you're reflecting it... If, A prime CB.
CB.
Yes. Oh yeah, it's just cyclic. You just know it's cyclic because the angles are the same by the time.
Hmm.
That's how you get A prime equals A prime C.
Oh, so what's it? You have which one are you saying? A prime.
A prime CB is cyclic.
A prime, CB. Okay, and then how does that get you what you need?
They're equal angles. A, B, A prime, C.
Yep, so they're cyclic because of the equal angles, right?
Yeah.
And then what? So
And that just gives equal sides.
equal sides.
So equal
Oh,
angles,
because you're saying it's
equal angles subtend equal sides.
oh
Right?
oh I see what you're saying now.
So what is he saying?
Oh, he's saying this angle stands on this arc, right?
Oh.
And this angle, so angle ABC, ABA prime stands on AA prime, yeah? And A prime BC stands on A prime C. So they should be on the same, they should be the same length because they made the same angle with the circumference. Yeah.
So we know BCAA dash is cyclic.
Yeah, BC A prime A is cyclic because the bow tie, because of these angles are the same, yeah? Yeah, that's one way to do it, yeah. Another way to do it is I think AA prime is parallel to BC, right?
Yeah.
So then that angle is the same, so it's isosceles.
Yeah.
Yeah, so there's two ways to do it. You can either go AA prime, BC is cyclic, and then the equal angles subtend equal chords. Or you could be like AA prime is parallel to BC, right? And then the alternate angles are equal. Hmm. But it's kind of a nice way to see it, right? The reflection.
Yeah.
Bro.
Okay. Questions? Alright, what's next? Should we load up another geometry?
Okay.
Actually, the question is FMC. What is FMC? FMC2. I'll find it. This is 2020 FMC 2, which is also a senior, which is the same as junior 4, yeah. So I want to show you some progress made by a younger student, and then see if we can finish it
Why
up.
is it called the final mathematical? What is it the final for?
And here it says second final.
Bro.
I don't know, but it's not necessarily an easy contest, this one. It seems like an international one.
Yeah. It's final.
Yeah, so you have a triangle ABC, yeah? With 60 degrees. At A. I'm hoping some people can finish off George's solution. So we have ABC, and then we have external angle bisectors.
There's a 60-degree angle.
Call that F. And then D is the foot of the perpendicular. And E is the foot of the perpendicular. Yeah. So O is the circumcenter of ABC.
So what are the angle placings? External angle placing? Oh, so you draw the two external angle placings
Yeah.
that are opposite to the angle A.
Yeah.
And then you draw perpendiculars from that.
Okay, so the question asks you to show that BOC, okay, and ADE, yeah, that those two triangles, their circles have one point in common, exactly one point in common.
The tangent to each
Yeah, basically, yeah.
Yeah.
Okay, so what I want to show people is sort of George's first part of this solution. So George showed that F was in fact a common point. Yeah. So the way he showed this was,
Which two circles?
huh?
Which two circles?
So we want to show that
BOC is DOE.
the circle ADE
AD.
intersects circle BOC equals F only. Yeah.
Just improve BOC and
Yeah. Yeah. So we have George showed that F belonged to the intersection. BOC. So basically that BOCF is cyclic. Yeah.
Yes.
Okay, so first we know that ADEF is cyclic, right? So that actually means that it suffices to show that BOC is F is cyclic. Yeah. So he said that this was 120. Yeah. And then can you see that this angle here is 90 minus B?
What's B?
B is this angle.
So circle AD, circle F.
Which angle?
This angle.
That's 90 minus B.
Yeah.
So the two circles. F.
Oh, 90 minus B on 2, sorry.
So what are we trying to show?
90 minus B
Over 2.
Yeah.
You should probably write the like trying to show on the.
I did.
Oh, okay, yeah. A, D, E, and B, C. The circumcircles. Oh, so they're like internally tangent.
Yeah.
Yeah, because because the external angle bisector is perpendicular to the internal.
Or just, yeah, the external angle bisector is half 180 minus b, right? Yeah. Because 180 minus b is the angle.
Yes.
90 minus b on 2 is half the angle, yeah? So that's from that angle bisector. So you get b on 2 here, right? And similarly, you get c on 2 here.
Yeah.
Right?
What's the deal? Wait, how do we get there?
Yeah, so the angle bisector cuts the angle in half, right?
Yeah.
So 180 minus b is the angle.
Oh, okay, so just the angle B.
Yeah. And the same thing on the other side makes the c on 2, right?
Oh, I see. And
then b plus c is equal to 120, yeah?
yeah, then you can use like external to find
Yeah.
ABF is 90 plus 2.
Yeah, so this angle here is 120, right?
Yeah.
So angle DAFE equals 120, yeah? So therefore this is 60.
Yeah.
Okay, that's good. Yeah, so I put it to the other students. Maybe can we try to figure out why this is the only point of intersection. That being said, Vietnam is hard law. I'm bad.
Wait, how much did he do with your 4 questions?
Well, probably not considering the comment, but we'll see.
I still have to tie up the loose end too.
Oh, someone asked, is F the excenter? Yeah, I suppose it is an excenter, yeah?
In-center, ex-center.
It's the A excenter, yeah.
So you just want to show that FO passes through the circumcenter DAE.
TAE.
I just have to show, I think you just have to show F, O, and A are collinear.
What?
F, O, and A.
No, A is the circumcenter. DAE. It's not.
Wait, what?
It's not.
I guess one thing you could show is you could show the F with the circumcenter as a collinear. Yeah?
Yeah.
Or you can say that DE is parallel to BC.
My bad, bro. A really. It's like D.
How does that help?
Ream's theorem.
Oh,
Like that's parallel with that, yeah?
yeah. Use, yeah. Seems parallel. see writing.
Cool. Shows O is in center.
In sense of what?
ABC. Alright, so O can't be the incenter of ABC, right? Or can it?
Wait, what?
I guess it can if it's isosceles.
Oh, can't.
Then OBA equals B on 2. Then O. Yeah, then it would all be collinear. Mm.
Isn't there some dilation?
What do you mean?
Like the internal.
Yeah, I mean, like the triangle BOC is meant to be in the end, I think, a dilation of triangle ADE if AOF is collinear.
Doesn't need to be, because ABC isn't isosceles. Doesn't need to be.
Is that I keep drawing a triangle very isosceles.
Prove that.
Yeah, like I guess O could kind of move along the circle too, right? But O is the circumcenter of ABC though, so it can't move um, completely freely. So I guess we know O lies on the center line with F, and we know OF in the center of that is collinear. Oh, what? That is kind of crazy, though, isn't it? But that would make it a diameter, wouldn't it?
What the fuck?
Like this is a diameter. Or maybe it is in line with the
It doesn't need to be though,
doesn't it?
because that would mean that OBF has to be 90 degrees, which means that BO has to
Yeah.
be an angle bisector, but that's not true.
That's very strange. Oh, you're saying BO does not have to be an angle bisector.
Circumference. Ring. Fuck.
Oh wait, I think I've done it. If you extend AD to BC,
Okay.
then you get those congruent triangles. Of course, it's a bisector, right? So the two.
So extending this one too.
Yep, and that just makes D and E the midpoints.
Let's call this X
Wait,
and Y, yeah?
what is happening?
Yeah, so XBD equals DBA equals bisector. That makes congruent triangles. That means that D is the midpoint of AX, D is the midpoint of AY, and that makes DE and
Slow down. So XDB, you're saying is XBD is congruent to BDA. Is that what you're saying? Or more than that?
Wait, how is XBD congruent?
because
BDA, yeah?
yeah, this angle is the same as this angle. That's 90 and 90.
Yeah.
Oh, I guess there's other ways to prove that D is the midpoint of AX.
So you're saying D is the midpoint.
And similarly, E is the midpoint of AY. By midline, they have parallel.
D is the midpoint of AX. And E is the midpoint of AY. Yeah?
Oh, okay.
Oh, and then DE is parallel, therefore,
D is parallel.
to BC. Oh.
How's D parallel to BC? Oh, D is the midpoint of. Oh!
Ah. And then, so you made use of the rings, you know, in the end. That's very cool. So this is Jeff. I have. So just in case you don't know what we're talking about, Ream's theorem is this. It's becoming a meme in this week.
The meme here.
The
Ream.
Ream of the week. Ream. It basically says that if you have a circle and another circle, and you draw lines like this, then the tips of the lines are parallel. Yeah. And you can take it in many different directions, but a special case of it is if you have a circle tangent to another circle. Well, the points of the intersection are now the same point, right? So they just come out like this.
Oh, so it's like a variant of like the dilation.
It is dilation, yeah? But we say reams because it's been the theme.
The theme of the ream is the ream.
Yeah. So of course, if the circles weren't tangent, right, then like I guess you'd have something like this. And they wouldn't be parallel, right? The circles that weren't tangent. If they came from the same point of intersection, they wouldn't be parallel, right?
What?
Hmm?
Do you mean? They didn't come from the same.
I'm saying this parallel condition is enough to show that they're tangent.
Oh, okay. Converse.
Yeah, I guess if you wanted to really do it, I mean, you just look at like a tangent line from there. See.
And at the same angle. It's just AST.
Yeah, so this angle is equal to this angle. It's equal to that angle.
It's just AST.
Yeah, I guess you got to do it without assuming they're the same point of contact. So you have to draw it like draw it like it'd be like that, right? Then you have this line, this line. They give you parallel lines, yeah.
Just the converse of the alternative.
Yeah, so you draw the tangent here, right?
And
The angle has to equal
has to equal both.
both, right? So it has to equal the angle of the tangent of the other one too,
Yeah.
right? Which is so it means that the tangents are equal, and this point doesn't exist. Yeah. Yeah. Instead of quoting Ream's theorem and expecting people to see how you applied it in a really weird way, I think it's better just to show why, like, if a tangent is if and only if these two lines are parallel, you know? It's easy enough to prove on the side. You know what I mean?
True.
Pretty good. Excellent. See, I knew we were going to get through that. Alright. Yeah, maybe we can do a brainstorm of two then, because I think Singh got most of the way. Yeah, William got a little bit of the way. I think Haibin said he got most of the way. Maybe we can try to finish off. I haven't looked at it yet. But you're interested in that too, aren't you?
What?
Functional one.
Question two.
A bit, yeah.
A bit.
A bit. He looks so demotivated. Maybe he needs like.
I mean, we still have some questions. I see. The options. I'm curious though.
Stop that.
It's making control.
I can't move this. Alright, what was the question? So the question was
for find all functions reals to reals.
so this is 2021 already, yeah?
Yeah, 2021 would be
They might not have done it in 2021, but the point is, stuff happens.
Before you know it, it will have happened.
Yeah. 2021 Vietnam 2. What was the question?
So f of x, f of y. F of x times f of y equals to f of xy minus 1.
Minus 1.
Yeah. Plus x of y
X f of y
plus y f of x.
plus y f of x. Is that it? That's the question?
I should probably check. It should be. Oh.
Okay, so what did you get? 0 is obviously a solution, right?
Yep.
So f equals 0 works. Oh, the identity doesn't obviously work.
So one observation that it's immediately symmetric. Okay, so just some easy substitution. Like try x and y both equal to 0.
Okay, sometimes we can, so this is what I saw some people doing. If you have pxy, is the statement that you can do like p of 0, 0.
Oh, is the point at 0, 0? Is that what I mean?
So f of 0 squared
Oh, we're doing the functional.
equals f of minus 1. Is that what you got?
Oh, yes.
Huh.
So now, well, we have minus 1. Wouldn't it be logical to sub?
Minus 1, is that what you're saying?
Um,
Sub one of them is minus 1.
but
The other
that
one is
might
0.
not be actually.
If you sub
Sub one of them.
sub one of them is 0.
Yeah.
You get something. You don't sub minus 1.
Yeah.
And is sub one of them 0, other one minus 1?
If you sub one of them is 0, then f
Oh.
of 0 is either 0 or f of y is f of 0 plus 1. So, but then yeah, that must be equal to 0.
Minus f of 0.
So use your first condition. Replace the f minus 1s by f of 0 squared, bring everything to one side and factorize. Get f of 0 is 0. Wait, what was that? Was that a count?
Huh?
Wait, I thought like on
Hmm.
the phone. Oh, like
Okay, if f of 0 is not 0, then f of 0 squared equals
this.
f of 0 minus 1. Wait, how do you get f of 0 is 0 here? Is this what you got?
So you
Oh,
replace
yeah.
F1. Oh,
Yeah, you divide it by f of 0, bro.
what?
Why did he divide by f of 0?
Oh, what just happened here?
Yeah, if f of 0 is... So if we assume f of 0 is not 0...
Yeah, you get that, which is no solution.
Oh, this has no solutions.
Because it's a quadratic. It's f of 0 squared minus f of 0 plus 1 is 0.
What are you talking about?
Oh, so this one has no solutions, right?
So F0 must be 0.
Because it's
Okay.
plus a quarter, plus 3/4, yeah? And this has no solution. So therefore f of 0 equals 0. Okay, good.
And f of negative 1 is 0 as well. Obviously.
Yeah, someone's got the hang of writing on the whiteboard pretty fast. Much faster than us.
Huh?
Someone managed to write, what if f of 0 was 0? Like, instantly. That's good. Oh. Okay. So back to the original equation.
So now we have f of 0 is 0 and f of negative 1 is 0 as well.
Oh yeah. Bonus. 2 values for the price of 1.
Yeah, now
Yay.
I'm stuck there.
Stuck.
I guess next is I try to find out what f1 is.
And you get it's either 0 or 2.
Yeah.
If
Oh.
it's 0,
Sub
then
in both of them as 1.
Did you try the linear? If you get stuck, you try the linear solution. Yeah, that's
There
a
are
good
no
thing.
linear solutions.
See, he doesn't know that.
Oh,
he
okay,
never
you
tried
didn't
that.
try it. Oh, bruh. I keep spoiling everything. That's why I have no friends at school.
What do you mean?
Because I spoil like every extension 2 problem like 2 hours before they get.
What? It says you shall not pass.
What?
That's pretty funny. It's like you shall. Have you seen that? Lord of the Rings.
I haven't watched it.
Wait, is this Finn? I would guess it's Finn. This must be one of the younger kids. It's pretty funny.
Oh no, we now only have half of the infinite plane to work with.
You can be sure it's not Leo. You can be sure Leo is not actually on the stream.
Contradiction.
That's why he's here so much. Because if he's not here, he won't log in. Yeah, it's funny because it actually makes it harder to pass. Oh, the new shall not pass got deleted. What? Does that mean I can pass now? Oh. Oh. Passed.
Okay, so you get f of 1.
Do you put in f of 1?
X and y are both 1. Just put that. You get f of 1 squared equals to, well, 2f of 1.
That's a 0, right? 2f of 1. Oh, that's pretty.
So f of 1 is 0 or 2.
F of 1.
It branches off into 2 distinct cases.
Oh, usually when it does that, there's 2 solutions it corresponds to.
Yeah.
So if it doesn't have 2 possible solutions, then you might wonder if it's actually branching off.
Because they both seem valid. So let's see what if f1 is 0, check the easier case first. So it's not.
That doesn't make any sense.
Huh?
that wouldn't be the easier case if you suspected all of them were 0, right? Like if you suspected there to be no other solutions but the 0 function, right? Then f of 1 equals 0 would be the harder case, because that would solve the problem in the end, right?
Yeah, I suspected it, but then I tested some other things. Found that, and no spoilers.
Yeah.
Found there was another solution.
Yeah.
So then I started. I started testing f1 and 0.
Oh, someone wrote my f of minus 2 equals 0 too as well. Wait, what if you just put f of 1 and 0 in? What do you get? So you get 0, minus 1, 0. You get 0. Oh, do you just get 0?
Yeah, you just get all zeros. Because f of minus 1 is 0, and f of 0 is also 0.
Oh. Oh, maybe it's Will. Oh, who is that?
You shall not pass.
I don't know if it's the same person. F of minus 2 equals 0, 2. Let's have a look. F of minus 2 equals 0, 2. How would you get that? You get 1 and minus 1? Is that what you did?
Wait. No,
If you do 1 and
I didn't
minus
actually
1.
get that.
Okay, f of minus 2
You just sub one of them is 1.
plus minus f of minus 1. Oh, so f of minus 2 is 0 if f of minus 1 is 0. Wait, f of 1 is 0.
Yeah. You can also get, so you just subs one of them is 1 and assume f of 1 is 0. Sub x equals 1.
Yeah, f of minus 2 is equal to f of minus 1. Is equal to f of 1. So if f of 1 equals 0, then f of x equals f of x minus 1. Or minus f of x minus 1. Is that what you said?
F of x equals to minus f of x minus 1. You have that yet?
What?
So if you sub x equals 1,
Yeah.
you get 0.
No, I think he had this.
Yeah, that way.
Or y equals 1. Is it the same?
Oh, it's the same because it's symmetric.
Okay. Well, that's good to know because.
So basically now.
Yeah, so if f of 1 equals 0, right? Then they get that f of x minus 1 plus f of 1 plus f of x, I mean. Yeah, so that's what they get. F of x equals minus f of x minus 1.
And then you use that in the original equation. Remember in the original equation there was f of xy minus 1?
Yeah.
You can use that.
Oh, because that becomes f of xy. Or minus f of xy, is that what you're saying?
And that observation pretty much solves the case.
Really? So you have f of x, f of y equals minus f of xy plus x fy
Wait, is still online?
plus y f of x. Alright, Jack, are you still tuned in?
What's going on now?
We showed that f of 0 equals 0, yeah?
Yeah.
Then we showed f of 1 minus 1 equals 0.
Yeah.
Now, and then we showed that f of 1 was 0 or 2.
Yeah.
we showed that f of minus 2 is either the same as f of 1.
I got that too.
And then we showed, so now we're assuming it's equal to 0, yeah?
Yeah.
If f of 1 equals 0, then you get f of x equals minus f of x minus 1. And then we sub that condition into the original equation. So this is, I guess, mostly Sing and blue writing guy. For this, right? Yeah. So then the equation becomes this.
Oh yeah.
You have the xy minus 1.
Yes. Yes.
And basically, after you get rid of the annoying minus 1, what you have to do is sub in like minus 2. Or sub in 2 or whatever.
Wait, what are you talking about?
So sub it into the new equation. Sub in like, we know f of 2 is 0, right?
F of 2 is 0.
Wait, we basically know f of all the integers is 0 from that.
Yes.
Oh, okay. You gotta say stuff like this before it's being used. So this is f of integers equals 0. Yeah?
Pick the most convenient integer 2. So
2
like,
is the most convenient.
yeah, because 1 and 0 are too trivial. So like 2, what's the best next?
No, it's because 1 and 0 have been used.
Yeah.
Yeah, it's not that they're trivial.
They're trivial. Have been used.
The 2 hasn't been used.
2 is like the first integer I've seen.
So you put x as 2, is that what you're saying?
Yep.
Alright. So you get 0 times that equals minus
f of
2y
plus 2f
plus 2f of y. Oh, that's...
So bring it to the other side. So this is f of 2y.
The 2 comes out of the top. So you get... f of 2y equals 2f of y, yeah?
But if you take the left hand side f of 2y, it's also equal to f of 2y minus 2.
F of 2y?
Yeah. Left hand side is f of 2y. So that's also equal to f of 2y minus 2.
You're saying this?
Yeah, using the condition twice. Because 2y minus 1 negates it, and then minus 2 flips it back.
I'm confused. What condition are you trying to use? You're trying to use this?
The f of x equals to x minus 1.
Okay, and then you use it with 2y, yeah?
Yeah, you use it twice.
F of 2y equals minus f of 2y minus 1 equals to f of 2y minus 2. Yeah?
But then the 2 pops out because of that.
So
f equals 2
y minus 1.
y minus 1. Then use it in reverse. So that's negative 2 f of y.
Oh.
And that equals to positive 2 f of y. So thus f must be 0.
Okay, so then f of... Yeah, so f of y equals minus f of y, right? And f equals 0. Would you look at that, Jeff?
What happens?
Okay. Glad we have your attention.
Yes.
Sometimes it's like a lot of attention or no attention. Yeah, so using this, right?
Yeah.
You put 2y for x. You get f of 2y equals minus f of 2y minus 1, yeah?
2y.
So apply the condition twice.
Yo.
Yeah. You do it once, yeah?
Wait, what condition?
This condition. The f of x equals minus f of x minus.
Yes.
You do it once to get minus 1, yeah?
Yeah.
You do it again to get minus 2.
Yeah.
And you apply this condition to pull the 2 out, yeah?
How'd you get that condition?
How do I get how do we get this condition?
Yeah.
Oh, so Zing got this. Do you remember how I got this condition?
Yeah.
And then Zing subbed in x equals 2.
Yeah.
And then gives you this condition.
So basically, x equals 2, that disappears, that disappears. 0 stored in one step. Both
2y.
plus 2fy.
Oh, cool. That's pretty great.
It's just so demotivating.
It's like, and
Can
then
you
we
do
get
it for
f of
any
y
integer?
equals minus of y. And then
Yeah, any integer works, but 2 is the most convenient.
so we do like f of y equals minus f of y, and then we apply the condition again, and we get f of y equals f of y. And no contradiction.
Well, as long as it's an integer, f of any.
Yeah, but 2 is the most convenient. You don't need the other one.
Sure.
Alright, are we at the same point now?
Uh-huh. Hmm.
Alright, so basically what we got is if f of 1 is 0, they're all 0, yeah?
Yeah.
So the only case when you consider is f of 1 is equal to 2.
Which
See if
is
there's any
actually the harder one because I haven't done it.
Oh. That's pretty good.
I tested the solution. I know the solution will come out of that.
Oh, wait, we got this.
Yeah.
Well, what are we doing now?
Wait, why are you subbing x equals 2? That's not.
Didn't we do that?
No, we didn't.
What do we do then?
So basically, you see the left-hand side f of 2x, right?
Where?
Here, f of 2x, that if you sub in the 2.
Yeah. Yes.
So f of 2x, you apply the condition of that, right? So it's twice. You apply the condition once, it becomes negative f of 2x equals to, the left-hand side equals to negative 2x minus 1. You apply it again, that becomes positive f of 2x minus 2. Applying that condition, you bring the 2 out, and then you apply it again once more to get minus 2f of x. What?
Don't you get this? Yeah? Just divide by 2 on
Wait.
both sides, right? Right?
Wait, no. That's 2f of x minus, wait,
So you just took the 2 out.
yeah, so yeah, that's right. You apply, so that's both equal. You see the like a bit of a contradiction here, because that's supposed to be equal to minus, but it's also equal to itself. So it's minus negative is equal to itself, so it's a 0. So if you scroll up, you have that, right?
Yeah.
But then you also have that, which is that minus.
Yeah.
So it must be 0.
Yeah, you could have gotten that another way.
You could, but
Because you just sub in 0 here and you get f of minus 1 has to be 0.
wait,
And you sub minus 1, you get f of minus 2 has to be 0.
no, but this is for all real numbers.
This is for all real numbers.
Yeah, this is for all real numbers. I never said x have to be an integer here. Your 2 is an integer, but your x is real.
Okay. Okay, that's good.
We already knew that all integers go to 0. And 0 for all x and real.
Cool. Now what?
Now let's do the other case.
Oh, so does this give you all integers of 0? So you have x equals 0, right? That gives you minus 1 is 0. And it gives you a negative integer 0. F of 1 equals 0. How does it give you? Oh, okay, you just use it the other way to get the higher ones. Yeah.
Yeah, because negative is like.
Yeah, like it's f of x plus 1 equals minus f of x. So, yeah, so that gives you all the integers. Okay, good. So now we're at this point where we're actually assuming. So f of 1, let me change colors. Red. So f of minus. So f of 0 equals f of minus 1 equals 0, right? And then we can basically assume f of 1 equals f of minus 2 equals 2, yeah?
So this seemed before I actually did anything, I first noticed this looks strangely like a quadratic.
Yeah.
So I tested.
Let's have a look.
So I tested the f of x equals to x times x plus 1 because the roots.
Wait, you can prove in general that f of x equals f of x.
That's also what I did.
Oh.
It's here. True.
Oh. Okay, f of x equals f of minus x plus 1. So, if you sub in y equals 1, yeah? So if you sub in y equals 1, you get f of x times 2 equals... Wait, not in general, but in this other case, right?
Yeah, in the other case, yes. Well, in general, technically also yes. Because they're all 0.
Oh, because they're all 0. Oh no, f of... Oh, okay, yeah, sure. Yep. Yes. Good logic.
Logic.
Alright, y
That
equals
would be
1.
like
F of
loading
1
at me.
is 2. F of x minus 1 plus 2 f of x and plus 2x. What? Wait,
Wait, 1 minute?
what just happened?
Hold up.
Wait, if you sub y equals 1, right?
Yeah.
You get 2 f of x equals f of x minus 1.
But where did the 2 come from? It's 1 f of x.
Wait, what's f of y equals 1? F of 1 is equal to
2.
2, right?
Yeah.
There's 2 f of x.
Right, 2 f of x, but there's only 1 f of x on the right hand side. It's 1 times f of x. Yeah, that's the...
Okay, and then...
You cancel that out, and you get f of x.
Is that right, though?
Yes.
This must be Will.
Huh? What happened?
Okay, then... Wait, so what was stated then? F of x minus 1 plus 2x equals f of x. Is that what you got?
Yeah.
Oh.
Yep. And then
Oh, that's a quadratic.
it is
Like squaring.
so
Plus 1. Oh.
Yeah, it's
Squared.
just feels like x times x plus 1. So I tested that and it works.
Oh, you tested what?
Y equals x, because if it's a quadratic, the only quadratic it could be is y equals x times x plus 1.
Plus 1. Because it gives you 0 for... And it gives you 2 for 1 and minus 2, yeah? So that works, does it?
Yep. Works in the original condition.
X minus 1 times x. X times x minus 1. X squared minus x squared plus x, yeah. Quadratic works, huh? Where is everyone?
Yes, you can also prove.
So Jeff, have you checked that the quadratic works?
Yes.
Jeff checks.
Huh?
F of x equals x times x plus 1 works. Because that's like the only quadratic that has 0, 0, 2, 2.
Because 3 points define a quadratic equation.
Does it work?
Yes.
Okay, it works.
Oh, Jeff, no.
The lowest in the head text.
Alright, we have to make a rule saying you can't touch other people, okay? No head patting, nothing.
True. That's why.
So basically, if your interaction with someone is for your benefit, you have to wonder if it's really for their benefit. Okay.
True.
Oh, someone's checking it really quickly. I like this.
Wow.
Whose handwriting is this? I'm pretty sure I can guess who it is by the handwriting. Let's have a look. How does this handwriting compare to that? Do you think it's the same? Jeff, would you say? Use your geometry by sight. Would you say this handwriting is the same as that handwriting?
I don't know.
It's Will, yeah. It's gotta be Will. When you say it's me, it sounds like you're saying the function is like revealing itself to us. It's me, the function f of x equals x times x plus 1.
Bruh.
Yeah, he's checking it, see? Yeah, he's checking it good. Yeah, maybe it's a better way than expanding because it's nicely factorized, see?
Yeah, it's actually really nicely factorized.
See, if this is nicely factorized as xy times xy plus 1 y plus 1, right?
Yeah.
And the right hand side, therefore, has a chance of being nicely factorized. So the xy nicely comes out, yeah? So the xy cancels. So then you just want to show that xy minus 1 plus y plus 1 plus x plus 1 nicely factorizes, right? And it does, yeah? Okay, good. Wait, never mind, it works. That sounds like a Sean. Oh.
Have you had enough experience that like you can just tell even but not even based on handwriting, just like based on how they phrase the sentences.
Yeah, so we checked it. It works. Yeah. The plot thickens. Yes. Actually, that looks like a lot like Sean's handwriting as well. Ah, where's Sean? Maybe we just missed Sean. Ah la la. Oh, so have you gotten any further than that?
I subbed a few things in, but like basically nothing further than what the idea is presented on that. Like somebody, I subbed like.
So you can't hope for it to be injective.
Yeah.
You can't hope for it to be surjective.
That's a quadratic.
But it could be like two, well, it has to be 2 to 1, right?
Injective above a certain point.
Yeah, and nothing should output. So the minimum value should be what? It should be like minus.
Wait, it should be just minus. Is it minus 1? Minus
A quarter.
a quarter.
You're right, yeah. The minimum value should be minus a quarter. And it should be output by x equals minus a half, right? Yeah. That's a nice value because that's a 1-to-1 point. You know, there's only one thing that has x equals minus a quarter. The output's negative a quarter. That's quite a bit of progress. Where is everyone else?
So I tried the same trick for like for the f1 equals 0 thing. So I subbed back into the original equation. So the original equation becomes f of x times f of y equals f of xy plus y f of x plus f of x of y minus 2xy.
Oh. Wait, did you tell him Uncle Big picked up at 3:30?
It depends on how long the stream goes.
Oh, okay. Not about Jeff after all.
Oh. It's just that like, because after 5, like after 6 o'clock, we don't usually do much. Anyways. Like, I think it's more efficient if I just like exercise at home and start grinding out some English because I have to do that. It's a necessity.
Yes, I think Will got 0 of f of 0. X squared.
Basically, I tried the same trick. The original equation become. Tried the same trick.
Oh, because you know how to minus 1 now. Yeah, I don't mind that. Let's do that.
I think also
Excuse me. Oh, what is the same? Huh?
Friends calling me. What's up? Yeah, I didn't bring mine. Or, wait, I'm not bringing mine, so can you bring yours?
So I guess the point of this is f of xy minus 1 is equal to f of xy minus 2x. Alright? Oh, so minusing 1 is like minusing 2x.
isn't it 2xy?
xy, yeah. Got f of x, f of y equals f of xy minus 2y. Yes.
What happened?
So we got from here. So we're using the same kind of thing to get the minus 1 out of the f.
Jeff be like,
I can't have a loss. Getting picked up soon.
Oh, but not your mom. Hey. You gonna break pit?
Yeah.
Alright, so that looks promising.
still playing against hopefully. Isn't this supposed to be the same game with the crazy amount of maths?
So here you don't know that the integer values give you 0 anymore.
I'm pretty sure you can still get like an integer that satisfies the condition.
Integers output integers.
What's that romantic?
Quality proof.
Yes, it's schizo.
Oh, so this is all you got?
Pretty much. Because like, didn't quite get to finish it. I saw you could just that was the point. I saw you could like take away two and like subtract two equations And for equations that you get f x equals f of minus x minus 1. So basically, you can get it symmetric about a half, about negative a half.
Oh, really? What can you get symmetric about a half?
Like the function is symmetric about a half.
How'd you get that?
Oh, basically
About negative a half.
about negative a half. Yeah. So from that you just sub in -1. And that
Here,
here in the equation.
you sub in -1.
X equals -1. Or y equals -1 doesn't matter.
Then -1 gives you 0, right? Wait, what did -1 give you?
0.
0, right?
Always.
Yeah. So then 0 equals f of minus y minus plus 2y, yeah? Plus minus f of y. Yeah? Like this?
Yeah, you go kind of like this, but then you see you have the plus 2y, but then you also have the plus 2y back when you solve x equals 1.
Mm-hmm. Mm-hmm.
So subbing x equals 1 into like the original equation.
What? Well, that's how we got this.
Oh, okay, yeah, we already did. Right. It's basically like a page of rough work. Oh yeah, you just add that to that, because see how many terms match up.
Oh,
Like
okay.
the
So
2x
make this
and
into an
2y.
x, yeah?
And then 2x and 2y, and then f of x and minus f of y. So
Okay, so f of y minus, so f of x, so replace x by y by x. So f of x minus f of minus x equals 2x.
add that to the big boxed equation.
So then f of x minus 1. Oh, there's someone else here.
Someone else
It's
wrote
clearly someone else.
Yeah, someone else wrote it already.
Oh wait, it's not clearly someone else. X of x minus 1 equals f of x minus x, right? Yeah. Which is like saying x minus a half is equal to a half minus x. Yeah? Yeah. Like if that's the case, then there is a chance of showing, for example, from minus a half onwards it's symmetric.
It's
Yeah.
injective.
Injective, yeah, that's what I mean.
And it should have to be because.
So you can, I guess you can kind of think of f now as going from minus a half to r, you know? Wait, did I do something wrong? So it's x equals minus a half, right?
Yeah, minus a half to r.
Oh, I did something wrong there. X plus a half. Hold on, I need to say something else. Wait, did we get f of x minus 1 equals f of minus x? Is that true? Negative a half.
What do you get? What did you say?
Wait, how did we end up with f of x minus 1 equals f of negative x? Is that right?
X minus 1.
Is that right?
By adding the two equations.
Equals. It seems to be true.
Well, nothing. I was looking. What's wrong?
Huh?
What's wrong?
Oh, I go soon. We gotta go soon.
Okay, so
Yeah, so how do we get from f of x minus 1 equals to f of minus x to that it's symmetrical across negative a half?
oh,
We should just add something, isn't it?
yeah, you just add a half to both sides of the x.
That's what we did before. So we got f of x minus a half, right? Equals
F of
x negative x minus a half. It's not quite what we want. I think what we want is we want f of minus a half plus x, right? To equal f of minus a half minus x.
outer drum, and when you added
Oh,
a half,
it is right.
you subtracted a half on the other side for some reason.
That's a minus sign.
Yeah, minus. You still.
Oh, it's right. It's right.
Yeah,
It
it's
works
right.
out. It's the same as this. Yeah, so that's why it's f of minus a half minus x, f of minus a half plus x. Yeah. Yeah, so that's like I think generally if you suspect that to be the answer, you can kind of try to prove things about it that narrow it down to that, yeah? So like you know it's symmetric. That actually helps a lot because now you can consider it
Injected.
almost injective, yeah.
Surgery. Almost. Can we? The next thing, just like you know how we in the f1 equals 0 case, we did all the integers first.
Yeah.
We try a similar thing here.
Yeah. So I think you get the integers give you integers.
Yeah, the integers all over the formula.
Yeah. Okay. Yeah, that's a good idea. Okay. So we have that f of x minus 1 plus 2x equals f of
X.
x. Yeah.
So we can do that by induction.
Okay, so suppose f of x minus 1 follows the formula, right?
Yeah. So that's x minus 1. It's fairly trivial. Plus 2x. So that's equals f of x, which means f of x is just x times x plus 1.
Yes. Ah,
The other way works as well.
yes.
For the negative.
So the other way works as well for the negatives. Indeed.
And of course, because it's symmetric.
Oh, okay. Well, that's good evidence, yeah? It'll make you worry less and less about other solutions. So this is on integers. We know it's true, yeah? Oh, so what does that suggest you could do next? I feel like there's a natural suggestion that comes off that.
You could try like a similar trick to what you did.
Yeah, why not, yeah? So what's that?
So your original trick was like you read my case 1 again.
No, no. It shouldn't need to be read. It should be important in your head.
Oh.
The important stuff should stay.
So again, if you sub in like an integer that follows the rule.
2, right? You
Yeah,
subbed in 2 last time. So you subbed in 2 for x. What does 2 output? It should output 6.
Output 6, yes.
6 f of x equals f of 2x minus 1.
2 f of 1.
6 x.
Okay, I'm gonna start. See you.
Oh,
Coming tomorrow as well?
alright, see you, Jeff. Oh, Jeff, take your solutions. I actually forget these every day.
What's the point of marking them if you keep forgetting them?
Oh, but he saw the smartphones. So
But like,
I'm not completely keeping up.
yeah, but like, the main point is I read over them and I read over what I might need to improve.
That's cool.
Okay, I'll get
Wait, Jeff, you got everything?
maths.
Oh. 6x plus 2f of x. Oh, actually, this is a pretty good condition. That's doable. Make sure you stretch and stuff before you go.
First of all, let's get by the way, by the time I showed it for the integral time, I'm already like putting away all my suspicion of the negative solution.
Yeah. Most of it.
Vast majority of the stuff.
Yeah.
Solution did a mid-base scan.
Yeah, the one you have there is pretty good. It looks a lot like something you have. And it's really good when something looks like it and you know it's not the same. And that'll give you something, right? If they're exactly the same. Well,
0 equals 0, yes! Function no equation. Completely messed up. 1 equals 2. Alright, I'll be. Oh, see you, Jeff.
So actually, you think you can get it from here?
Like, again, like the 2x minus 1, you can kind of.
Yeah. It'd be better if you got it instead of me doing anything.
Oh, yeah, sure. I'll just try and do it from here. So, what we have, so now we have just f of. We know it's symmetric. X. Okay, so now what for? Let's just put the right up in the corner for a while because I don't want to actually. I don't like how like when you write things up, like it's kind of different from when you're actually solving it. Let's just put the right up away for now. Okay, so
Yeah, we have infinite paper here. So
infinite amounts of paper.
yes.
Okay, I'll probably go like F5 or what I'm probably this is probably the last problem I'll do.
Okay. Yeah, just make sure your mom knows.
So yeah, we can. So basically, the induction shows it's for all. Claim is true for all integers.
Yeah, which is really good.
By the way, this on our extension 1 paper, there was like, why can't you prove a real number by induction? Like, there was actually a question. Like, why can't you prove the claim for all real numbers by induction?
No, it's obvious, I guess.
Not obvious. And then like nobody actually, like only a few people actually got it.
Not countable.
The teacher actually got it wrong.
What?
Like honestly, he said like, because it's not an integer, you can't induct it.
But isn't that what the question's asking you? It's a tautology.
And he says like, it has
Yeah.
nothing to do with countability.
What?
It's like what? He said because it's an, but like, and I made a remark after class. It's just like, no, it's wrong. Like if you can like induct, you can induct, for example, every half or every quarter.
Yeah.
Like, or any countable set you can induct over it.
Yeah.
He's like, no.
What? I see. Not evidence based.
Davies. Teacher of the going to drop extension 2 class.
Oh.
There's like the top extension 2 class, like half people, but like then there's the going to drop extension class, which like averages like a fail.
I see.
It's like there are way too many people in that course.
Right. So when's your mom coming?
Like 4:30.
4:30. Okay. So you got an hour to do this.
So an induction. And how many questions did Haibin get? 3?
Oh, I don't know.
Induction claim is true for all integers. F of x is equal to x. We can do a similar trick here. So we have subs the x equals 2. F, F, 6 2 minus. Was this the like that mess up somewhere? Oh, okay, I didn't. Well, I messed up on that. Basically, 4 f of y equals to f of 2y minus 1. What's that? That's just f of 2y minus 4y. Is it 4y? It is. Isn't as obvious as the f of 1 and 0 case where you just flip it twice. Also, but you have the f of 2y, so I guess all the fractions now work. Like all the 1 on halves, the quarters, the halves, the quarters, the eighths, they all work.
Why is that?
Because you can sub them in here.
Yeah, I suppose.
So basically,
Hmm.
so now you have like the annoying thing is you have the f2y and the fy.
Yeah.
This is also true for all the like the rational thing.
Oh yeah.
Because like you don't have to sub in 2.
Hmm.
Sub in anything. I think it was this. Try this idea. And then sub in f of 4 is 20. Pretty sure this one gives fine. This should F1 10. Yeah, this one, it's the same thing. No wonder Hyping said it's hard, isn't it? Who's that?
It's my mom.
Oh.
You okay?
Oh, excellent.
Oh. Oh. 2019 AMO.
Yeah.
Wait, why is it a silver? Didn't I get? Didn't you give me the bronze thing?
That was for 2020.
Oh, did I get silver for 2019?
Think so.
What? Why? Well, like, if I had got a silver for 2019, I would be invited to camp. Makes sense.
Yeah, but we're talking about just last week.
Oh. Oh.
What was 2019?
Oh, that's why it's like. Oh, the one that I got like 5 solutions for?
Yeah.
And like 6 solutions.
Yeah, I can't remember which paper it was.
Pretty much 5.5. That was some steal. But yeah.
Which questions are those? I can't remember. Oh. Oh, what's this?
What happened here?
Yeah, where was our formula for the 2x part? I think so. It's f of x times 6 equals f of 2x minus 1. Plus 2 plus 6x. Hmm? I think this could be equal to 4.
Are those medals right, Michael?
Yeah, they're good. Yeah.
Wait, what?
This is my dad. He printed them.
Oh.
Yeah.
Wow.
He made them. Yeah, they're really good, Shane.
So we got it for all the integers and all the rationals. So what more could it take?
Of course, it's going to be there when you come back.
What more could it take?
Minus 2x minus 2.
the function is continuous
Hmm.
and it's true for all rationals, does it make it true for all reals as well?
Oh, oops. 8x minus 2. I'm a little confused. That's 4 f of x minus 1 plus 6x. Is that right? Hmm. Oh, so that does get you back to basically where you started.
Yeah. Find it. But doesn't it suffice to show that the function is increasing?
No, does it?
Because we showed it for all rational.
So?
It's because the rationals are dense in the reals.
Hmm.
So if some real number is out of place, then it would be like, if it's increasing, it can't be out of place because it will be like out of place for the next rational.
I'm not sure. Because at the moment it's doing like this, right?
It's like lots of dots on a parabola.
Yeah. But it doesn't have to be as, it could be zigzagged up, increasing, you know? Still increasing.
Because you can find the rational on the line.
Hmm.
Like, because they're dense, so you can find a rational in one of those zigzags, and it will be higher than the real after it, if that real is out of place.
No, it's still increasing. The zagging is still going up.
So, you have like this parabola like this. Say a real was out of place.
Yeah, so this gives you back the original condition.
Yeah.
This one here. How come it worked last time?
Because there wasn't no 2x term.
I'm not convinced.
And remember last time it actually flipped it. That was the crux of the argument last time. It was when it went from 2x to 2x plus 1. Like, flipped it. before it, like flip the sign.
It's not an explanation.
What do you mean?
Like, why did before? Like, this is a tautology now. Before, a new piece of information existed, which is harder to do, right? Because there's less information to be had. Mm-hmm. I guess one difference was we took this one out first. Mm-hmm.
I noticed something really interesting.
Mm-hmm.
If you factorize this is an interesting kind of multiplicativeness to the function.
Mm-hmm.
So if you factorize, if you move these terms to the left, you can actually like factorize it like this. F of x minus x is f of y minus y, f of xy minus xy.
Really?
Multiplicative. Difference between its function input and output is multiplicative.
That is interesting.
Well, you can see it's satisfied by the x times x plus 1.
So you're saying alright, so if you have x, f of x times f of y. You can factorize that. Minus that's what you're saying.
I think it kind of narrows it down.
It certainly is a nice expression, huh?
Because you can basically define like g of x to be f of x minus x.
Yeah.
Get a multiplicative function.
So g of x is multiplicative.
And we want to prove that it's x squared. Nicely x squared.
Oh. You want to prove g of x is x squared. Is that right?
Feels natural.
Multiplicative. Took a log of f of x.
What's a log?
I'm just thinking how log works. If you took log of f of x.
G of x.
G of x, yeah. Then log of g of x plus log of g of y is equal to log g of x g of y. go again. You have g of x and e of g of x log g. That was a good substitution for multiplicative functions. I can't remember how to do it now too. G of 0 is 0. G of 1 is what?
1 is 1. It's still
Really?
the rational thing still presents.
G of 1 is 1.
Again. Because when output and input is multiplicative. So,
G means and it works for positive.
First irrational number I see this working for is like the golden ratio. Like it's reciprocal as it's -1.
G E. Yeah, this is probably not the intended way to solve it, but I think your multiplicative thing gives you something.
With the logs.
Yeah. But you should carry on doing your thing, because this is probably not the way that question 2 Vietnam was intended.
With the wait, did you solve it?
I think so.
But like, don't really want to go like unintended.
Yeah, like I'm not really after the solution. I just pursue interesting avenues.
I'm also trying to use a multiplicative thing. If you have a real number and it's inverse.
Not quite this. It's something else.
Does this give you something? Twigs, man. Okay, so the g function is going to be even. Then.
I need log g. It's in conjugation.
喂，差不多5点吧。哦，这题有点那个什么麻烦。再见。 This property is pretty nice. F of y plus f of negative y is 2y. Because the g function's even.
Oh, you're doing G now?
The g function's even, but I'm going back to f because it's f of y. So the x squared plus x, that satisfies this condition.
Yeah. Once you translate it to the G function, I think the approach is pretty much like I can solve it once you do that. I'm pretty sure. Like it kind of sets out what you have to do. Yeah, like I'll explain it later. You keep doing it your way, but basically, if you change it to G, right, you can just use the Cauchy functional equation.
Oh.
Yeah. You just need one transformation to change multiplicative to additive, and then
With the longer.
yeah. But I don't know if it's a. I don't know. Like, there's definitely going to be a more kind of down to earth way as well.
Yeah, that seems real. The Cauchy thing.
That might be interesting to talk about tomorrow.
F of y, 2y.
I'm just gonna go to the toilet.
Remember output. An output that we can. Oh, so it's really. That minus x, then you get 2x. Yeah. Yeah. Literally. True. Instant solve. It's an instant solution. Good log. What? What happened? There's no point. Take this. Functions increasing. Wait, this is not polar. So much.
fraction?
No. Okay. Well, I have to go in a bit. I believe this actually turned out to be. Wait, if we prove the function is increasing, aren't we done?
Yes. Yes.
Yes, because the rational thing.
I don't know if it's because of the rational thing. But yes, I don't think so.
We got any ideas on the stream?
I think they're giving up.
They're Plants vs Zombies.
Hmm.
Right. I mean, we're only missing like one thing.
Just a little bit to go. I'm coming at 5.
Probably. So you have the g of x. The g of x you know is even.
Yes. Mm-hmm.
So what does that tell you about f of x? So f of x plus f of minus x is equal to 2x.
Mm-hmm.
So
Yeah, the g of x idea is good. See what happens if you just re-express all the things in terms of g. G is
f of x, the output
so
minus
f
input.
is g plus y. F of x is g plus x.
Mm.
G of x plus x, yeah. X g of y plus y. G of xy plus xy minus 2xy plus x g of x plus y plus y g of x plus x. Yeah? So what do you get? G of...
So I notice all the xy terms cancel actually. G of x, g of y. Wait, whose is this?
Yeah. I don't know. So they're kind of on the same wavelength as us. So g of x, g of y plus x g of y g of x plus xy, yeah? Equals all that. And cancel.
Cancel, cancels.
Cancel, cancel.
Cancel, cancel, cancel.
X g of y, x y g of x
Yes.
cancel, yeah?
And minus 2xy and minus 2x with xy, xy.
Oh, like this, yeah?
Yeah.
Oh, so we exactly get g of x, y equals g of x, y. Is that right?
Yeah, that's the multiplicative thing.
Yeah. So that's like literally the only condition on G. Like G and F are equivalent, right? There's an invertible transformation.
That means it's gotta be like, if it's multiplicative and like the other condition is when you add it, it's even.
That's strange, huh?
Yeah. Like you're supposed to get, it has to be x squared.
It's multiplicative. It's even, so it's enough to... How'd you get it was even? Some other condition.
Oh, it's yes, there's some other condition.
It's multiplicative. It doesn't imply that it's even, right?
No.
Wait, what was... Someone else...
It's multiplicative and even. So that's all you literally get. The thing is.
Oh, wait a minute. Was that the original condition? I think I did something wrong here. F of... Wait, f of 2x... f of xy, hold on. F of xy minus 1, right?
Yeah.
That's g of xy minus 1
Plus
plus
xy mod.
xy minus 1, yeah? There's a minus 1 here. So if it was just the original condition, would it be g of x, g of y equals g of xy minus 1 minus 1? Right, that's maybe we did it not so correct. Why did I write it like that? So this plus x g of y plus y plus y g of x plus x. Yeah. So this cancels from there. xy is 3 xy's. There's only one xy there. You get 2 xy's left. So you get g of xy minus 1 plus 2xy minus 1 equals g of x g of y. Yeah, like the reason is like the multiplicative is not enough to determine that it's x squared, right?
Mm-hmm.
So there has to be like multiplicative plus some other condition, yeah?
That is even.
No, it's not enough. So it's whatever this other thing is, right? Because what happens is all you have to do is exclude the Cauchy case, remember? The Cauchy functional equation, yeah?
Oh yeah.
You just have to exclude the case that it's dense. Yeah?
The circle thing.
Yeah. I don't know how you remembered it like that, but anyway, so you just have to exclude the case it's dense, right?
Mm-hmm.
And you need some other condition that's not just multiplicative to do that, yeah? So that's going to be something like this, yeah? Because that one is slightly different than multiplicative, but it implies multiplicative, right? So it's something more specific than multiplicative, and that'll be enough to give you the answer.
So how do you get? So you got that from the original functions equation.
Yeah, I think that's what I was trying to do just then, but for some reason I subbed in f of xy minus 2xy there, which is not what I wanted to do. Yeah? Yeah, so if you want to do it all again, yeah? Yeah, that's what, yeah. This person has the right idea. As soon as I go there, they erase.
Bruh.
But yeah, it was the right idea. So it was gx gy, right?
Yeah.
Plus xgy plus ygx plus xy equals gxy minus 1 plus xy minus 1 plus xgy plus y plus ygx plus x, right?
So ygx and xgy cancel out.
Yeah, so this
that.
and this cancel with this and this, yeah? And that cancels with this. You get gx gy equals gxy minus 1 plus 2xy minus 1. Wait, was there a minus 1 missing somewhere?
No.
Ah, yeah, good. So it's basically these two conditions, yeah? Is that -1 really there? Seems strange. Oh yeah, that's right. This is the condition for G. Yeah. Because it was 2x for f, right? But when you put it to G, you get a -1. Yeah, so basically you just need to show using these two conditions, right?
Yeah.
That G is not dense. Well, it's not quite that G is not dense. But like, for example, if you show that G is increasing, right? It also shows that the other function is increasing. Even if you show G is decreasing, it's fine.
It just depends on which half you pick.
Yeah. So G of positive is always positive, see?
Yeah. But if you're solving two positive numbers, like x and y, just any two numbers, you'll get G of that number is plus -1. So it's 2x.
So maybe this is the way you're meant to go, even though it seemed obscure. So all you have to do, right, is to eliminate the crazy functions, and then you have it by the Cauchy. Yeah? You know what I'm talking about?
Yeah, the crazy, like the everywhere functions.
Yeah. Functions which are dense. So one way to eliminate it, for example, is if it always sends positive numbers to positive numbers.
Already?
Like the additive one.
Oh, okay, not the multiplicative.
Yeah. Well, the multiplicative one, I think you need the ones bigger than 1 to go to bigger than 1. So, like, for example, can you show that g of x is greater than 1?
That's easy.
Is it?
Because look, x and y, if xy is bigger than 1, bigger than 1, then that g would, then it will be bigger than 1, the right hand side. If x is less than 1, there will be less than 1.
Which equation are we talking about here?
The bottom equation.
This one?
Yeah, so x and y, if xy is bigger than 1,
Yeah.
then g of xy minus 1 is going to be bigger than 0.
Yeah.
And 2xy is going to be bigger than 2. It's bigger than 1.
Oh.
And if it's vice versa for less.
So if g of x, does that work? So if g of x is greater than 1 for all x greater than 1, right? Is log of g of e to the y greater than 0 for all y greater than 0. Yeah?
Yeah.
So if y is greater than 0, right? Then e to the y is greater than 1, right?
Yeah.
If e to the y is greater than 1, then g of e to the y is greater than 1, right? And if log of g of e to the y then has to be greater than 0, right? Yeah?
Yeah.
So we don't even need less than 0 equal to 0, just greater than 0, right?
Because we already know how.
Yeah.
0 has to be 0.
Yeah, and we've done this before. So this is when you have a function like h, right? X plus y equals h of x plus h of y, yeah? Then because they're going from r to r plus, right? Yeah.
Yeah.
Then it's increasing,
Oh.
right? Yeah, the r plus to r plus is OP because it automatically gives you that h of x plus y is bigger than h of x.
Yeah. So the log is increasing.
Yeah.
So the log function, it has to be increasing because it sends r plus to r plus and it's additive.
Yeah.
So gxy must be greater than gx.
No, the hx y h. Yeah. Yeah, I suppose it would also make g increasing, wouldn't it?
Because it's just a log.
Yeah. Is it obvious that g is increasing as well? Not as obvious, is it?
Right. Why is it not?
I mean, like, just originally.
Originally, it wasn't. Once you do that, it becomes obvious.
Yeah.
Because g sends greater than 1 to greater than 1.
Yeah, but if it's multiplicative and it sends greater than 1 to greater than 1, that should probably mean it's increasing as well. Because if you have g of x, g of y, right?
It sends less than 1 to less than 1, yeah.
Equals xy, and it sends greater than 1 to greater than 1, right?
Yeah.
So you just need something greater than x, right? Just times it by something, right? It's greater than 1, yeah? You know what I mean? So g of z is bigger than or equal to g of x. Is bigger than g of x, right?
Yeah.
You times it by some y bigger than 1, right?
So the function is increasing.
Yeah, and because g of y is greater than 1, g of z will be greater than g of x. Yeah.
And if it's increasing, you're done because this epsilon delta, this some whatever definition. Like for example, if you have
Yeah.
if you have like some real number that's out of place.
Yeah. So I guess the official thing would be like there's no dense because if it's increasing, right?
Yeah.
Like at this point it's the maximum up to that point, right? So it's bounded on this interval, and that is not dense on that interval. You know what I mean? That's like the official way to do it. You know what I mean?
A little like unofficial ways.
I feel like the reason I didn't suggest this to you, well, I did, but I didn't pursue it, was because I thought this was just an aside. But once you have that G is multiplicative, is pretty much the only condition. This becomes like the main way to go.
So this is essentially like the main solution.
I guess it's weird though because what if you didn't see it? I think you still have to find some. You could still find some other way if you didn't see this.
Because you have to see that factorization, which is not easy to see.
What does it say?
What?
At sing cater.
Cuteness is a Cauchy function.
Oh, what?
Oh, it's an inside mean. Basically, like, it's will.
Oh, it's Will.
Yeah.
Yeah, I didn't think Haibing would say something like that, but I thought Haibing would know that more than Will would. So this actually solves the problem. Do you want to see how it finishes?
Oh, yeah.
Or you know how it finishes?
Yeah, I kind of pretty much know how it finishes. So basically, now we have it's increasing.
Yeah, so it's Cauchy then, right? It's the trivial Cauchy one.
Yeah.
So you have log of g of e to the x
what?
is equal to
log.
lambda x.
Oh.
Yeah,
Bruh.
it's literally that trivial, yeah. And then log
Wow.
of g of do something.
E to the y.
E to the y. Okay, sure.
Yeah, like so e to the x, e to the y.
Oh.
Wait, we already done that.
No, this is lambda's a constant, right?
Yeah.
Thanks. Assist.
Logs of G.
So it's easy to find the constant, right?
Yeah.
Because we know that like when x is
When x is 1,
well, we'll keep it with the constant one. We'll just find the constant at the end. How about that? Yeah. What do you do from here?
so we get rid of the log first.
Get rid of the log, yeah.
Yeah.
Right, that's what you mean. G of e to the x
Equals e to the
lambda x.
lambda x. Yeah.
Yeah.
Now, like the lambda on the outside.
Yeah.
E to the x to the lambda. Consistent. Then that means just gx equals to x lambda. Same thing now.
Yeah, for all positive x,
Yeah.
right? Gx
And we
equals
know it's symmetrical, so we only need positives.
yeah.
So
And we know x is 0 gives you 0.
what's lambda now? You can just easily find lambda because now we have the condition.
Yeah, so g of x equals x to the lambda. So we're gonna have to sub in something that's not like
Trivial.
1 or 0, yeah? To detect the lambda.
Well, we know like 2.
So what was g of 2?
G of 2. F of 2 was G of 2 was 4.
Yeah?
Yeah.
So g of 2 equals 4.
Now that means lambda is 2.
Yeah, so lambda equals 2.
Gx equals x squared, and hence f of x equals to x squared plus x.
Yay.
A
X squared plus x. Yeah. Can you see actually the write-up would be like 1 page?
well, not 1 page because you you have that other stuff as well.
No. It always seems hard when like you write out all the working and show all the things, but like yeah, I mean Vietnam isn't easy, I guess, but it doesn't mean that. See, one of the reasons I guess we didn't see this instantly is because like, oh, Koshi seems like it would make it too hard. Yeah. Like, so you were working on something else and I did the Koshi thing or whatever, right? But it could have been intended this way.
Yeah, it wouldn't really be a 1 page because you still have the. This is for f of 1 equals 2.
Yeah, but that other stuff didn't take a whole page, did it?
It took 1 page.
Yeah.
This stuff, the other stuff, you have to first get f of 0, then you have to get like this stuff.
Yeah, maybe we'll do like a write-up or something. Give just a shorthand of the solution.
Yeah, so using the original condition, not the truncated condition, was like the main like breakthrough. Because once you have a truncated condition, you usually don't think to use the original condition anymore. Okay, excuse me. Is my phone in there, or do you have to like give my phone a call or something?
Phone has been lost.
Right. Wait, is it in here? Is this in somewhere trivial?
I think Vietnam has 300 million people, is that right?
300 million people. Like close to. Wait, really?
I think so. They usually have a pretty good IMO team.
Yeah. It's definitely.
But having said that, like if you're used to that kind of difficulty, it might not be hard to pull it off in the contest. There it is.
Let's put it on the ground. Oh, it's in the back. Oh, it's not in the bag. It's down here in the slot.
You see it?
Yeah. Okay. That was fun. 喂，啊，做完了。好，再见吧。再见。 Wait, what? Can Z go to?
No, he's ain't going now. He wants to go to dinner.
Who?
I'm still thinking it's Will.
Yeah, I think the main, like, actually, I think if I would have used Kalshi, the rest of it was pretty intuitive.
Yeah.
Used Koshi, but I think the main thing is, like, figuring out the factorization.
Yeah, that was a key step.
Yeah, like, actually
Yeah.
observing
It was
that,
a
like,
senior moment in the opposite sense of the phrase senior moment.
yeah, what's a senior one?
Or like traditionally it means like old people forget their lines or something.
Oh!
But I'm trying to say it as like the opposite. It's like a dumb moment, but I'm
like
trying to say
pulling,
it's a smart moment.
it's pulling a stupid. It's called pulling a ringo.
Yeah, but this one is like pulling a smart because you pulled the smart. That once you did that, I knew it was solved. I just didn't know that's pro. I didn't know that was how it was intended to be solved. But I think there are questions where like some contest problems like a senior would have a quick way of doing it like that, and a junior would have to struggle but still get there. Like
Because like the fact it was not obvious.
Yeah, Haibing said that too, definitely.
Wait, Haibing said that factorization.
No, he said there's probably a more standard way. And I'm trying to say that too, yeah, definitely. Because when you put it as question 2, right?
Yeah.
If there's only like Koshi can't be the only way because that's too unfair for people who don't know Koshi.
Like even without Koshi though, like if you just have the idea, like you can just prove it for all rationals and say it's increasing.
Yeah, let's say we're still looking for a more elementary solution.
I was kind of like, I felt like the multiplicative thing was like, the real big brain moments are usually you don't realize them at first. Like when I like did the factorization, I said like, oh, this probably doesn't mean much.
Mm.
So the ones you often don't realize them. I guess Vietnam too is well the couch. Jordan. Is anybody coming tomorrow?
Hopefully, we'll see.
Because Vietnam is like so many people. It's like 10 times more people than Australia.
Wait, let's look up how many people Vietnam has.
Yeah. To make the difficulty of the AMO is of the National Olympiad is proportional to its population over its population.
Oh, it's only 100 million.
Oh.
But I remember doing all the questions in Thailand. Thailand might have put more people. Thailand.
Remember, Vietnam is just like a tiny strip.
What?
70
Thailand's
million.
only 70 million. Jeez.
Like, remember, those are tiny countries.
But traditionally, their IMO teams are so much better than ours.
We have like 25.
Yeah, but we have like kind of like a special demographic of high-level immigrants.
Bro. Still, like, usually the problem with high-level immigrants is once they come here, they come here to seek a more low-level field of expertise.
Yeah, and then the kids leave to another country, possibly never to come back. Alright.
Ah.
Good seeing you.
That was pretty good. That was pretty good. Maybe I'll try.
Just here. Oh, fine.
Maybe I'll try question 3.
Yeah, go for it. So we've got one more, and then the next week is just rest and consolidation. Some of the ones that have been left behind, I'll show you other solutions. Basically, get those questions out of your mind.
Still, I don't want to lose. Like, AMO geometry traditionally has been pretty.
Why is it doing complex math?
Huh?
Why are they doing complex math? So get out of jail.
But if it's
Time card, it's not free.
Oh, it costs a hefty amount of time investment.
Yeah. So you have to be good enough to be sure that you can actually. That's why I've been doing it the whole week. Right?
And also, you have to be good enough in other areas that you have time to use it.
Yeah.
You have to pay like a hefty payment of time. Actually.
Right.
Hopefully, I'll come back.
Right.
See you next time.